It starts with a vibration you feel in your teeth before you hear it in your ears. The gauge needle climbs. It passes 180, then 200. It trembles, then locks at a number the operator has never seen before. He lunges for the safety valve, gripping the iron handle slick with grease. He pulls with everything he has, but the handle won't budge. In the next 4 seconds, 3,000 horsepower of superheated steam tears through 6 inches of riveted iron. It launches a 40-foot boiler through a brick wall like a cannonball. The blast throws men 150 feet across the rail yard. The building's 3rd floor pancakes into the machinery below, burying 23 workers under tons of twisted steel and scalding water. This is March 1905, and this is how an ordinary Tuesday becomes a mass grave. But here is the part that makes it worse. This wasn't an accident. Every gauge, every rivet, every safety system had been deliberately compromised to squeeze more power from a machine already pushed beyond its limits. So the question isn't whether this explosion could have been prevented. The question is, how many people saw it coming and said nothing? To understand this carnage, we have to go back to where it started. We have to understand the engine that drove the American century. The American factory floor in 1880 ran on a single, brutal truth. No steam, no money. For decades, industrial power was a prisoner of geography. You built your mill next to a river and you prayed. You prayed the water didn't freeze in January, and you prayed it didn't dry up in August. But the post-Civil War industrial boom demanded something fiercer. It demanded a power source that didn't care about the seasons. The stationary steam boiler answered that call. These machines were architectural in scale, 30 feet long and 8 feet across, holding thousands of gallons of water heated to 200 degrees Celsius under 150 pounds of pressure per square inch. They were monsters. 1 boiler could power an entire textile mill. 2 could drive a steel foundry's rolling equipment. 3, arranged in a battery, could keep a locomotive factory running 3 shifts without pause. The economics were irresistible. Install a bigger boiler, run more machines, hire more workers, capture more market share. But the pressure, both literal and financial, never released. Factory owners faced a binary choice. You could operate at design capacity and watch your competitors outpace you, or you could push past the red line and multiply your output. Most chose the latter. They connected boilers in series. They fed them cheaper coal with higher sulfur content. They delayed maintenance shutdowns because downtime meant lost revenue. What happens when an entire industry decides that maximum capacity isn't enough? The boiler room becomes the factory's literal and metaphorical heart, a chamber where heat, pressure, and human desperation concentrate into something unstable. The men who tended these iron giants worked 12-hour shifts in temperatures that reached 120 degrees. They shoveled coal into fireboxes that glowed white. They watched gauges that measured forces capable of tearing steel. Their job wasn't to keep the boiler safe. Their job was to keep it running no matter what the needle said. By 1890, and more than 100,000 stationary boilers operated in American factories, and the number climbed every year. Each one held enough energy to level a city block, and each one operated under the same unspoken rule: production over caution, profit over safety, output over everything. The stage was set, and the pressure was building. A boiler shell looks solid until you understand how it's made. It isn't a seamless vessel. It is a patchwork. Thousands of hand-driven rivets hold overlapping iron plates together, each one hammered hot into pre-drilled holes by men working in teams of 4. The 1890s standard called for rivets spaced every 3 inches along a seam. But this was manual labor, prone to human error. Miss one hole by a 1/16 of an inch, and you create a point where metal flexes unevenly under pressure. Let a rivet cool crooked, and the seal begins to weep. Multiply these small errors across a 30-foot shell, and you haven't built a fortress. You've built a structure that is only as strong as its weakest connection. Let me take you to Hartford, Connecticut in 1854. The Fales and Gray Car Works boiler explodes during a routine morning startup, killing 21 workers and injuring 50 more. Investigators recover fragments showing rivet holes drilled off-center, allowing steam to force its way between plates. The company had accepted the boiler from the manufacturer without independent inspection. The shell was defective from the day it was installed, but rivets are only the beginning. Water chemistry attacks iron in ways most operators never see. Let water sit stagnant and oxygen begins the corrosion process, pitting the interior surface. And feed a boiler with mineral-heavy water and scale builds up, a rock-hard crust that insulates the iron from the cooling effect of the water itself. The metal overheats. It softens. Under constant pressure, it begins to bulge like a bubble of gum. Inspectors in the 1890s routinely found boilers with plates worn from half an inch down to the thickness of a dime, still in daily service because shutting down meant lost revenue. What does a factory owner see when he looks at these warnings? The boiler inspector from Massachusetts reports finding 347 boilers in dangerous condition during 1893 alone, with 89 ordered immediately removed from service. Yet records show that 34 of those condemned units returned to operation within 6 months, their owners having made minimal repairs or simply moved them to facilities outside the inspector's jurisdiction. The evidence is physical and damning. Recovered boiler fragments tell stories their operators never lived to share: cracked welds, sheared rivets, corrosion patterns that follow water lines like rust-colored maps. These aren't mysteries. These are predictions written in metal, ignored until the moment they come true. The man who controls 3,000 horsepower rarely knows what he's controlling. Most boiler operators in the late 1800s received no formal training. They learned from the previous shift worker who learned from someone before him, creating chains of knowledge based on habit rather than understanding. A new hire might get 3 days of observation: how to shovel coal, how to check the water glass, how to crack the blowdown valve once per shift. What he doesn't get is instruction on metal fatigue, pressure dynamics, or the physics of steam. He's told to keep the needle in the green and the water above the red line. Everything else is feel. Let's go back to Braidwood, Illinois on February 16, 1883. The boiler at Diamond Mine explodes during the morning shift change, killing 69 miners waiting to descend. The operator had noticed the pressure gauge climbing, but assumed it was temporary, a pattern he'd seen before during cold snaps when demand spiked. He didn't know the safety valve had frozen shut overnight. He had no training to recognize the danger. The inquest records his testimony. "I thought it would settle down like it always does. But how do you measure the weight of responsibility placed on men who can't read the gauges accurately?" Survivor accounts describe the impossible calculus. If you shut down for suspicious noises, you're labeled overcautious and risk termination. If you push through and something fails, you're blamed for negligence. The Chicago Tribune reports in 1890 that the average boiler operator earns $2.50 per day and works 6 days per week. Factory foremen, paid on production bonuses, routinely pressured operators to keep steam up regardless of conditions. The knowledge gap kills in predictable ways. Operators mistake scale buildup in water glasses for safe levels, not understanding that the mineral crust blocks the true reading. They hear banging inside the shell and assume it's normal thermal expansion. They watch safety valves weeping steam and pack them with rags to stop the leak. These aren't acts of stupidity. These are decisions made by men working with partial information in an environment where caution costs jobs and boldness keeps families fed. And then there is the safety valve. It represents engineering's answer to human greed, and it fails almost immediately. The principle is elegant: a spring-loaded valve set to open automatically when pressure exceeds the boiler's rated capacity, bleeding excess steam before the shell ruptures. It is supposed to be the final line of defense, the mechanism that makes catastrophic failure impossible. In practice, it becomes the first thing factory managers tamper with. The methods vary, but the goal is identical. Some owners wire valves shut with steel cables, preventing them from opening at any pressure. Others file down the valve seat, creating gaps that let steam leak constantly at low pressure, convincing operators the valve is functioning when it's actually disabled. The most common modification involves adding extra weight to the valve's lever arm, forcing it to stay closed until pressure reaches levels 50 or 75 pounds above the boiler's design rating. Why would anyone deliberately sabotage the only device preventing an explosion? Because every pound of additional pressure means more power transferred to the factory floor, more machines running, more product manufactured per shift. Insurance company records from 1895 show that 62% of investigated boiler explosions involved safety valves that were either modified, disabled, or improperly maintained. The Hartford Steam Boiler Inspection and Insurance Company reports examining 4,471 boilers in 1896 and finding safety valve defects in nearly half of them. The numbers don't suggest carelessness. They suggest a system where safety mechanisms are treated as obstacles to profit rather than protection against death. Brockton, Massachusetts knows shoe manufacturing, but March 20, 1905, teaches it something else entirely. The R.B. Grover Shoe Factory employs hundreds of workers across 4 floors, most of them women operating stitching machines and presses. The building sits at the corner of Main and Kalmar Streets, a dense industrial corridor where factories pack shoulder to shoulder. At 7:45 in the morning, and 3 stationary boilers in the basement explode simultaneously with a force that registers on seismographs in Boston, 12 miles away. The blast vaporizes the boiler room, collapses the first floor into the crater, and sends upper floors pancaking downward. Workers on the 3rd and 4th levels fall through disintegrating floors into a pit of scalding steam, shattered brick, and twisted machinery. The building's north wall blows outward, showering the street with debris. Witnesses 3 blocks away describe a sound like artillery fire, followed by a rolling cloud of white steam that obscures the entire block. Rescue crews arrive within minutes, but can't approach for nearly an hour. The steam is too hot, the structure too unstable. When they finally enter, they find bodies stacked in stairwells where workers had rushed toward exits that no longer existed. Some victims are identified by jewelry, others are never identified at all. The final count reaches 58 dead and 117 injured, making it the deadliest boiler disaster in Massachusetts history. What could cause 3 separate boilers to fail at the same instant? The State Inspector of Boilers reveals a cascade of negligence. The boilers, installed in 1890, had never received professional inspection. Water treatment was non-existent, allowing scale buildup that reduced heat transfer and weakened the iron through overheating. Safety valves on all 3 units were found weighted beyond their design specs, set to release at pressures 40 pounds higher than the boiler's rated capacity. Most damning. The plant superintendent had been warned 4 months earlier by his own maintenance crew that the shells showed signs of bulging. He ordered the crew to stop mentioning it. The explosion kills instantly, but steam takes its time. Superheated steam at 200 degrees Fahrenheit doesn't behave like boiling water. It exists as an invisible gas carrying enormous thermal energy. When it contacts human skin, it condenses instantly, releasing that energy directly into tissue. The result is burns that penetrate through multiple layers in seconds. Medical literature from the period describes these injuries with clinical precision. 3rd-degree burns covering 60, 70, sometimes 80% of the body surface. Skin peels away in sheets. Muscle tissue cooks. Survivors describe the sensation as liquid fire, a pain that doesn't fade, but intensifies as nerve endings die and then regenerate. Dr. William Warren Potter, treating victims of the Park Hill Shoe Factory explosion in Haverhill, Massachusetts in 1898, documents the progression in the Boston Medical and Surgical Journal. Patients arrive conscious and speaking, their injuries not yet fully apparent beneath clothing. Within hours, the skin begins to separate. Fluid loss leads to shock. Infection sets in almost immediately, turning wounds septic before any meaningful healing can begin. Potter reports that of 23 patients admitted with severe steam burns, 19 die within 5 days. Why does steam kill more effectively than flame? The answer lies in heat transfer. Steam carries roughly 5 times more energy per unit volume than hot air. When it contacts cooler skin, it releases that energy instantaneously while condensing back into water, which then continues to burn. Fire burns the surface and moves on. Steam penetrates and lingers. Hospital records from boiler explosion victims show recurring patterns. Many die not from the initial burns, but from secondary infections, pneumonia caused by inhaling superheated vapor, or kidney failure from the body's trauma response. The New York Times reports on December 13, 1902, that following the Abendroth brothers' boiler explosion, 8 men initially survived the blast only to die over the following 2 weeks. Doctors had no effective treatment. Morphine managed pain. Saline solutions addressed fluid loss. Bandages stuck to melted tissue, causing additional trauma during changes. The medical profession of the era simply lacked tools to treat injuries this severe. Survival often came down to the percentage of body surface affected. Everything else was suffering and time. Insurance companies started counting bodies because each one cost money. The Hartford Steam Boiler Inspection and Insurance Company, founded in 1866, became America's first systematic investigator of boiler failures. Their agents arrived at explosion sites with notebooks, cameras, and measuring tools, documenting everything from shell thickness to rivet spacing. What they discovered wasn't random mechanical failure. It was a pattern. The same causes appear in report after report. Owners deferring maintenance. Operators pressured to exceed rated capacity. Safety valves deliberately compromised. By 1895, Hartford's chief engineer, Charles Pierce, testified before the Massachusetts legislature that 90% of boiler explosions result from preventable human decisions rather than inherent equipment failure. The numbers tell a grim story. The National Board of Boiler and Pressure Vessel Inspectors estimates that between 1880 and 1910, American boiler explosions killed approximately 2,000 people per year. That's one explosion killing or injuring someone every 4 hours, around the clock, for 3 decades. Individual incidents might claim 2 lives or 20, but the cumulative toll rivals major battle casualties without the public attention. Just when the public thought they understood the danger, Greenpoint, Brooklyn, 1910, showed them a new kind of horror. The American Manufacturing Company operated a sprawling factory complex covering 2 city blocks. But the boiler room sat in a 3-story corrugated iron building. Chief Engineer Edward Corcoran arrived early to conduct his routine morning inspection. He found everything in apparent working order. At his desk 100 feet away, his wife glanced out the window and saw him sitting comfortably in his wooden chair, hands clasped behind his head, taking a brief rest. It was the last time anyone saw him alive. The explosion lifted a 40,000-pound boiler vertically through 3 floors and the roof. The massive cylinder became airborne, arcing over the factory yard before crashing into vacant ground near the riverfront, several hundred yards from its moorings. How does a boiler weighing 20 tons achieve flight? The physics are identical to rocket propulsion. When the shell ruptures catastrophically at the bottom, pressure releases in a directional vector. If the break occurs at one end of a vertical boiler, the intact end becomes the nose of a projectile driven by escaping steam. The force is enormous. Investigators later calculated that the energy release equaled several hundred pounds of dynamite, detonating simultaneously. Corcoran was vaporized. The bodies piled up faster than the laws could pass. Labor unions and reform groups demanded government intervention throughout the 1890s. The American Federation of Labor submitted testimony to Congress in 1902, documenting almost 1,500 boiler-related deaths over the previous 18 months. Factory owners countered that mandatory inspection would stifle American manufacturing, driving costs up and competitiveness down. Massachusetts became the testing ground. In 1907, the state passed the nation's first comprehensive boiler inspection law. Factory owners immediately challenged it in court, arguing the law violated property rights. The Massachusetts Supreme Judicial Court upheld the statute in 1908, ruling that public safety supersedes private property concerns when the danger extends beyond factory walls. This decision created a legal framework other states began to copy, but implementation proved uneven. Between 1907 and 1920, an estimated 18,000 additional Americans died in boiler explosions while the legislative process dragged on. But what truly ended the era wasn't just the law. It was technology. General Electric and Westinghouse began mass-producing industrial electric motors around 1910. The advantages were immediate. Individual machines could run independently. Maintenance became simpler. And most importantly, electric motors don't explode. By 1915, new factory construction increasingly specified electrical systems over steam, and the era of the massive stationary boiler began its slow decline. We end where we began, in that moment when the gauge needle climbs past red and an operator reaches for a valve that won't move. But now we understand every decision that led there. Every warning ignored, every safety measure defeated by the calculus of profit. The massive stationary boilers are gone, retired to scrapyards and industrial museums, but they left something behind. Every safety regulation we have today, from the sticker on your water heater to the protocols at a nuclear plant, traces its DNA back to this era. The courts established a precedent that still holds. Employers cannot prioritize profit over human survival. We know now that the right to operate a business does not include the right to create a lethal weapon in the basement. We know the cost of ignoring the needle, and we know that some pressures must never be allowed to build.